All right, hello everyone, and welcome to our third lesson of Unit 5 on concentration changes over time. Today we are looking at reaction orders and how we can identify those on different types of graphs. So the reaction order is identified by finding which concentration time relationship produces a linear graph. So a straight line for concentration versus time is going to indicate zero order. A straight line for the natural log of concentration versus time is going to indicate first order, and a straight line for the reciprocal of concentration versus time indicates second order. The rate constant for a reaction can be determined from the slope of an appropriate concentration time graph, depending on which order the reaction is. In a first order reaction, the half-life is especially important because it is constant and independent of initial concentration. And so it's directly related to the rate constant by the equation T half is equal to 0.693 divided by K. And radioactive decay is a classic real-world example of first-order kinetics, illustrating the constant half-life behavior. Graphing concentration versus time is going to help us identify reaction order because each order is going to have a distinct shape. So as you can see from the graph, we have our blue zero order reaction. That's going to show up as a straight line because the rate is already constant. Now for our first and second order reactions, which are red and yellow, those are not linear because their rates are going to depend on concentration, which causes those curves to either decrease exponentially or hyperbolically. So this is extremely important because a non-linear graph means that we cannot find the rate constant from concentration versus time. So we have to manipulate the data in order to make a linear regression. So for first order reactions, we are going to take the concentration and take the natural log of it versus time. And for second order reactions, we are going to take the inverse of our concentration versus time. To determine the rate constant K, we need a linear relationship between concentration and time. So we are going to adjust that y-axis depending on the reaction order. So zero order reactions produce a straight line already when we compare concentration versus time. So we do not have to change the y-axis for zero order. For first order reactions, those are going to show an exponential decrease in concentration. So plotting the natural log of the concentration versus time is going to form a linear regression. Then for second order, those are decreasing hyperbolically. And so if we plot the inverse of the concentration versus time, that is going to straighten that curve. So each of these adjustments is going to come directly from the integrated rate law that is on your reference sheet. So I posted that on the bottom right corner of this slide. And these are in order. They're not labeled, but they are in order. So if you were to get your reference sheet at the beginning of your AP chemistry test, I would just jot down 0, 1, and 2 so you can remember this is zero order, first order, and second order. So it kind of gives you a little cheat sheet to remember that zero order is just concentration, first order is natural log, and second order is the inverse. All right, and this is a great summary of the three graphs that we are focusing on today: zero order, first order, and second order. As you can see, the only thing really changing in terms of the axes in these graphs is the y-axis. So with zero order, we just have concentration versus time because as we increase our concentration, nothing is happening to the rate. But with first order, we take the natural log of our concentration, and that's because as we increase concentration of our reactant, our rate is increased proportionally to that. And then for second order, we take the inverse of concentration, and that's because as we increase concentration of our reactant, the rate is going to depend on the square of the concentration. So let's deep dive into zero-order kinetics in relationship to a concentration versus time graph. So in zero-order reaction, the concentration of reactant decrease at a constant rate over time, meaning the reaction rate does not depend on the concentration of the reactant. So when concentration of A is plotted versus time, the result is a straight line with a negative slope that's equal to negative K. And the relationship follows the linear equation concentration of A at a certain time equals negative K times time plus a concentration initially. So A sub 0 is going to be the initial concentration, and A sub T is going to be the concentration at a certain time. So the rate constant K can be found from the slope of the line or by calculating the change in concentration divided by time. And just remember your units for K. For zero order, that is going to be just concentration per unit of time. In first order reactions, the rate depends directly on the concentration of reactant, so the concentration decreases exponentially over time rather than at a constant rate. So taking the natural log of the concentration is going to make this relationship linear. And when we take the natural log of A and plot versus time, the result is going to be a straight line with a slope of negative K. And then we can take that integrated rate law from your reference sheet and we can manipulate it into K, or we can solve with a graph using slope. And then finally, just remember for first order reactions, the units for K is just 1 over the time, or time to the negative first. All right, and then in second order reactions, the rate is going to depend on the square of the reactant concentration. So when we plot concentration versus time, it's going to decrease hyperbolically. However, if we take the reciprocal of that concentration, we are going to form a linear regression with a positive slope. So again, we can look at our reference sheet and find our integrated rate law and put that into y equals mx plus b, and we can just solve using slope, or you can isolate K with the equation in the box here on the left. And then just remember your units for K in second order is going to be 1 over concentration times seconds, or whatever time value you're using, or you can write it as shown here. Using the data provided, determine the reaction order and then calculate the value for K with units. So remember in 5.2 we were given concentration differences and we were also given rate. Well, we're not given rate here, we're only given time versus concentration. So in order to decide which reaction order it is, we can plot the values on X and Y axis and see if it provides a straight line, and if it does not, then we know it's either first or second order. So we can manipulate those concentration values to see which produces linear regression. So first, instead of actually plotting the values on X and Y axes, I just look at the data and I look at the concentration values, and if they are changing by the same amount every single time, I know it would create a line on a graph. So right now, if I look between 0 minutes and 100 minutes, I have a change of 0.3378. And then if I look at the difference between 100 minutes and 200 minutes, I have a difference of 0.265. So I know it is not zero order. If it was zero order, those two numbers would be the same. So now let's go ahead and check if it's first order. Remember, with first order kinetics, which is here, we are taking the natural log of our concentration. So let's go ahead and just do the first 4 numbers and take the natural log of those. So I took the natural log of my first 4 values and I got 0.223, negative 0.0919, negative 0.407, and negative 0.722. So if I take the difference between my first two values, I end up getting 0.3149. And if I take the difference of my second two values, I end up getting 0.3151, which are the same numbers or close enough, which means I know these differences are the same, so they would form a line on an X and Y axis. So that is telling me that this reaction is first order. Now, AP Chemistry is only going to be testing you on 0, first, and second for these types of questions. So if you did that work for the natural log and it didn't work, you can just assume that it's a second order reaction. So now that we have the information of first order, we can go ahead and calculate the value for K with units using the information given. So using my first order kinetics integrated rate law from my reference sheet, which I already identified here, I'm going to just solve for K. So that's going to be the natural log of concentration of A, which in this case is CH3CH2Cl. And that's going to be at a certain time. Let's just call it 100 minutes. Minus my natural log of my initial concentration, which is going to be the natural log of 1.25. And then that is going to be over negative T. And T, since we chose 100 minutes, will be 100 minutes. So now let's go ahead and plug everything in. So I already got the natural log of my concentration at 100 minutes. So that is negative 0.0919 minus my natural log initially, which again I already calculated. So that is 0.223. And then I'm going to put that over negative time. So it's going to be negative 100 minutes. And when I plug that into my calculator, I get 0.00315, and this is a first order reaction, which means my units for K are just inverse of time, which is minutes, so it'd be minutes to the negative first power. So now I know that it is first order, and I also know my K with its units. So for first order reactions, the half-life is going to be constant, meaning it does not depend on how much reactant you start with. So the half-life is defined as the time required for the amount of reactant to decrease by 1/2 of its original value. And for first order kinetics, it's given by the equation half-life is equal to 0.693 divided by K, and that is given to you in your reference sheet right under integrated rate laws. And because this equation contains only the rate constant K, changing the initial concentration does not change the time required for half of the reactant to be consumed. So whether the starting concentration is high or low, each half-life takes the same amount of time. And just to be clear, on the AP Chemistry exam, half-life calculations are only tested for first order reactions, making this constant half-life behavior pretty important to recognize. All right, so let's do an example FRQ on half-life. This one says the radioactivity of a sample of I-131 was measured. The data is plotted on the graph below. Determine the half-life of I-131 using the graph. So here on the graph, we can see that we're starting at 16,000 decays per minute. So if we want to know how long it takes for the half-life, then we need to see how long it takes to reduce 16,000 by half, which would be 8,000. And the answer to that is 8 days. Then part D says the data can be used to show that the decay of I-131 is a first order reaction as indicated on the graph below. Label the vertical axis of the graph above. So we know for first order, and if you don't remember, just again go to your reference sheet. And if you look at first order, you can see that it's the natural log. So when we are doing a linear relationship between concentration and time, and it's a first order reaction, it has to be the natural log of the concentration. So the answer to I would be the natural log of the concentration of I-131. Then part 2 of D says, what are the units of the rate constant K for the decay reaction? We know our units for K for a first order reaction is just going to be the inverse of time. So in this case, we have days as our time. So it'd be days to the negative first, or you could also write it as 1 over days. They would accept both. And then part 3 says, explain how the half-life of 131 can be calculated using the slope of the line plotted on the graph. So it's really important here. You don't actually have to calculate anything. It's just telling you to explain how you would do it if you needed to calculate that. So the first step is you have to get the slope or the value of K first. So once you get K from our graph, then you can plug that into the half-life equation, which is T half equals 0.693 divided by K, and that's on your reference sheet. And before we wrap up this lesson, let's do a couple practice problems on half-life. Now, all 3 of the example problems we're about to do are technically multiple choice questions, so I think it would be a little bit easier. However, I do want to test our knowledge by not giving you the options and making you just find the answer to the question. So this one says, after a certain pesticide compound is applied to crops, its decomposition is a first order reaction with a half-life of 56 days. What is the rate constant K for the decomposition reaction? Now we already have the half-life equation from our reference sheet, so if we are solving for K, we're just going to manipulate this equation. So it's now K is equal to 0.693 divided by the half-life. And we already have the half-life, which is 56 days, so it'd be 0.693 divided by 56 days. And that is going to give us 0.012 days to the negative first power. If 87.5% of a sample of pure iodine 131 decays in 24 days, what is the half-life? So the way that my brain solves a question like this is I start thinking about how much of a sample is taken away after each half-life. So I know at the first half-life, I am taking away 50% of that sample. And at the second, I'm taking half of 50, which is 25. So at the second half-life, I now have decayed 75% of my sample. Then if I take 25 and half of that, that would be 12.5%. Now totally, I have 87.5% of my sample decayed, which is exactly what was given to us in this question. So now I can see I had 1, 2, 3 half-lives. And so if I have 24 total days divided by 3 half-lives, each half-life was 8 days long. So that is the answer to the question. AP kind of describes it in a different way. So in this first example, if 87.5% of the sample decays, that means that 12.5% of the sample is remaining. And 12.5% is going to be equal to our half-life raised to the third power, which means 3 half-lives have passed. And so if we take our 24 days and divide that by our 3 half-lives, again, that's going to give us 8 days for each half-life. The second question says, if the oxygen isotope O20 has a half-life of 15 seconds, what fraction of a sample of pure O20 remains after 1 minute? So when you're given a question like this, the first thing you should notice is that we have two different units. So since our half-life is in seconds, we should convert 1 minute into 60 seconds. And because we know our half-life is 15 seconds, we have 4 of those that can occur in 1 minute. So because we now know that 4 half-lives have passed, we can take 1/2 and raise it to the 4th power, and that's going to give us 1/16 remaining. All right, I hope this video helped. If you have any questions, please feel free to ask or reach out, and I'm happy to help you. I hope you have a great day. Bye.